All right, everybody. So we're getting into some rotational motion. We just did conservation of angular momentum. Okay. And when we're dealing with conservation laws, remember what we're interested in is an initial state and a final state. We don't care what's in between. For this stuff, we care what's in between. Okay. So let's start with our gear here and just put down some relationships, okay? And I'm not sure how many of these we've talked about before. Some of them will certainly be new, okay? But we've got our gear, and there's a distance around on the outside of the gear from here to here, all right? And we say that that distance S is subtended by the angle theta. Okay, that's the language that we use, all right? So we would say that S is equal to R times our delta theta or R theta, just like that. Now, if we start to take derivatives, okay, the derivative of the position is going to be a tangential velocity, okay? Now, if the radius doesn't change, so we're just talking about something like the gear, an object turning, okay, then we have R theta dot. But R theta dot is R times omega. Yeah, this is the same omega we used for angular frequency in physics. There is a reason for that, but we're not going to go into it. Okay, but what we've got here is that the tangential velocity is equal to r times the angular velocity omega. If we do another derivative, then we're getting the tangential acceleration. Again, we're going to assume r doesn't change, so that becomes r omega dot, like so. And but that is an acceleration, an angular acceleration. So the tangential acceleration out there on the edge is r times alpha, just like that. Okay. So what I'm going to do, I'm going to put those all in kind of a different place because we may be referring back to those, and I need that little black space over there. So I'll just write this down real quick. Okay, so the main thing, take home things for this part is that distance around is r theta, um, a tangential velocity is r omega, and our tangential acceleration is r alpha. Okay, now grab my eraser, make a little workspace over here, get rid of some of this. There we go. All righty. Woohoo! That was crazy, huh? Blow this back up. There we go. I'm sorry, was out of control there for a second. Um, Now let's talk about some of our most basic equations that we have used many times before. All right, most notably these guys. So we have SAM, which is V final, V initial plus A delta T. Bumblebee, V final squared. Oh, I'm really sorry, guys. That is off out of the range. Let me try this again. Here's Sam, Bumblebee, I'm still off the page a little bit. Sorry. And then Optimus Prime. like this. Okay. Our rotational equivalents are like this. So displacement is either like an x value or a theta value. Okay. Velocity term is either how quickly it's translating or how quickly it's turning, or an acceleration versus an acceleration. All right. So we can go both ways with that. Now, because they're all ultimately related to derivatives, and these are all for constant acceleration conditions, then that means we can write down that we have the rotational equivalent of SAM, which is going to be omega final is omega initial plus alpha delta t. Okay, we just substitute that guy in there. And our equivalent for Bumblebee here. So we put a delta beta instead of a delta x. And then our equivalent for Optimus Prime is this guy. All right. So those are all equivalents there. Okay. Now, there's another set of equivalents that we need to write down, and that is our relationship where we said that A, the acceleration, was equal to a V dV ds. Okay. That was very useful, remember, when we were talking about an acceleration that was not a function of time, but a function of distance or location somehow. We have the rotational equivalent as well, which is alpha is going to be omega d omega d theta. Okay, just like that. So you need to write all these relationships down. This is sort of like our introduction to it. And then in the next video, I'll show you how to apply this stuff to this particular problem. Okay.